In this video, we're going to do an example problem in biostatistics where we're going to use the chi-square goodness of fit test. We are testing how well what we observe fits with what we would expect under a null hypothesis. Now, as always, I do these problems with pen and paper, but stick around to the end because you'll see me use ChatGPT just to do the problem for me. Now, leave a comment down below. Tell me how you feel about using ChatGPT or another large language model as far as helping you to learn or to verify your work. Let me know about it. So let's take a look at this problem. The proportion of the population of people who have had peripheral vascular surgery due to chronic arterial insufficiency who believe that continued smoking puts them at risk for amputation is thought to be 0.6 or 60%. So people with peripheral vascular disease due to smoking, it's usually in the lower limbs and the legs, the arteries narrow due to atherosclerosis, and they develop all kinds of symptoms. And what you can do is to improve the blood flow, and there's various surgical techniques to do that. But if they continued smoking, the disease can progress. Other reasons for the disease to progress as well, and that might lead to amputation. So they were just this question was put to this population. Do you believe that if you continue smoking, that would put you at risk for amputation? And it is believed under the null hypothesis that 60% of this population thinks so. So researchers collect data from 100 random subjects in the population. And from those 100, you can imagine just a survey question, 55 of them said that continued smoking puts them at risk. So the researchers want to test the claim that the population proportion of these people who believe that continued smoking puts them at risk for amputation is not 60% using a 5% level of significance. And we are instructed to use a chi-square goodness of fit test for proportions to test the claim that the proportion is not 60%. So we need to generate this solution, and we're going to do that, of course, with our 6 steps. So what I want to do, of course, always in this case is I want a step 0, which is just going to summarize what we know. So let's put step 0. And step 0 is our summary. Under the null hypothesis, we have the following. We say that that's 0.6. This proportion of people who believe that continued smoking, from this population who believe that continued smoking puts them at risk. So I'm going to say p sub 0. We have a p hat. We have a p hat in this instance, and that is going to be 0.55 because 55 out of the 100 did that. Now, a different way to write this would be nice for a z-test proportion, but another way to do this is the following. Let's say the following. We're going to say that group 1, let's put it out there, group 1, that's going to be those that say yes. And we're going to have group 2, those that say no. Okay. And so observed, for those who said yes, we observed 55. And the observed for 2, that would be, of course, 100 minus 55. So 45 out of those 100 said no. And I have to work out what's the expected value for this group and what's the expected value for that group. Now let's think about it. If I have n equals 100 people and I expect 60% of them to say yes, 100 times 0.6 leaves me with 60. So I would expect 60 out of 100, if 0.6 was indeed true, to say yes. And if we then look at this must be, well, it must be 40. Again, it must be 100 times 1 minus 0.6, or 100 times 0.4, which gives me 40. So there I have my observed values and my expected values. And the chi-square goodness of fit test, what it's saying, how well does that which I observe fit with that which I expect under the null hypothesis? So do remember these expected values for each one of these. It's going to be, if I have 100 people and I expect 60% of them to say yes, 60% of 100 is 60. And then 40% of 100 is 40. And then, of course, we have our alpha value of 0.05. We have enough information to tackle this problem. So let's start with step number 1, which what we're supposed to do is we need to know what is our population parameter of interest. So we're going to say the proportion of, we're going to say people who have had, I'm just going to write it out and then I'll edit this so you don't have to watch me write. So there you go. I've put the proportion of people who've had surgery for PVD, is what we usually write for peripheral vascular disease, who believe that continued smoking puts them at risk for amputation. That's our parameter of interest, this proportion of people. So let's write this out at step number 2. We're going to write our null and alternative hypothesis. So let's have our null hypothesis, and let's say that we symbolize this. The symbol for this symbol is P. Okay, because we have a binary variable, we don't have to worry about subscripts. We're just going to take that this P represents this proportion of people. We're going to say that this proportion equals 0.6, making the alternative hypothesis that P is not 60%. It's different from 60%. And so that's very easy for this test. So step number 3, we're just going to say the level of significance alpha is 0.05. That is our willingness to falsely reject the null hypothesis. Given that the null hypothesis is true, that's our type 1 error rate. We're happy to reject the null hypothesis. We're happy to make that error, and I'm saying this in a little bit of jest, of course, with quotation marks. So let's have step number 4. In step number 4, we're going to say what test we're going to use. Well, we said we were going to use the chi-square goodness of fit test. We usually write GOF, goodness of fit test, but please write it out. I'm just being slightly lazy there. Chi-square goodness of fit test. Now, what do we need to be able to use this test? What are these assumptions? Well, we have a variable with a nominal level of measurement, because people could just say yes or no. So the variable that we have, variable is nominal. So that's important. We can calculate frequencies, and that's what we need. There's our frequencies. We need these people, these individuals to be independent. And we do need identical distribution. I'm just going to say identical distribution. What we're saying there, that if I take every single subject of this 100, that the probability that this person says yes is 60%. Next person, the probability that they say yes is 60%. I don't have a bunch of individuals, and that probability changes from person to person. And then finally, and let's put that in green because this is going to be an equation, I have to have that I have for my expected values for each one of my categories has to be at least 5, so 5 or more. So I really want all of these, and I'm just going to say E sub I must be greater than or equal to 5. By that I mean all of these. The expected value for the first group, expected value for the second group, that's all got to be larger than 5. And it is, it's 60 and 40. So we have enough people here that we can use this. And of course, we should also then say none of these proportions, none of these probabilities of proportions, and we only have the 2 of them, is close to 0% or 100%. And we certainly don't have that. We have 60% and 40%, so that's fine. So in step 5, let's calculate or state our test statistic, and we're going to say how it's distributed, what model we're going to use to describe this. So we're going to say our test statistic is x squared. Now, in most textbooks, they also use the chi symbol there, but I think it's good because we had t and we have z just to put x squared, but we can say that's described by the chi-square distribution. Now we need to know what the degrees of freedom are. So it has to be, it's a parameterized, so nu is our degrees of freedom, and in this instant nu is going to equal k minus 1, where k is the number of categories we have for our nominal variable, and we have 2 categories, so 2 minus 1 is 1, and I'm just going to say x squared is described by this distribution, of course only under the null hypothesis, so that's very important to put. So let's see what we get. For nu, at least for us, that's going to be 2 minus 1, that equals 1. So we're going to have that x squared is described by the chi-square distribution on a single degree of freedom. And so let's calculate this, but first let's have that equation. And our equation says that x squared is equal to, we're going to have the sum from I equals 1 to k, so how many there are, of observed I minus expected I, and I'm going to square that, and I'm going to divide by, let's have a nice streaks here as the ink is so wet, divided by, that was fine, expected for each one of these. So I'm going to go to group 1, then group 2, and I know what it is. Observed 1, expected 1, observed 2, expected 2. We have all of that. So let's just have that right here. I'm going to say what is my observed is 55. I expect 60. So it's going to be 55 minus 60 squared divided by 60. Plus, then I observe 45 minus I expected 40 under the null hypothesis. I square that. and I divide by 40. And there we go. And if you plug that into your calculator, see if you get the same as me. When I use my calculator, I get 1.0417. Okay, that's a measure of how good what we observe is to what we expect, the goodness of fit test. So let's do step number 6. So there's our step number 6. We need a critical value. We need a chi-square critical value. So what is that going to be? Or you can write the x-square critical value. Well, we need that for nu equals 1 degree of freedom, and alpha equals 0.05. So once again, you can use your spreadsheet software. And be careful, there's a difference, I think, between Excel and, say, Google Sheets with the probability that you have to put in for that formula. But for a single degree of freedom, it's 8.341. And what we have, if we want to reject, we must have that x squared must be larger than this critical value. And in this instance, we have, what was our value? 1.04. And that's not larger than. So in our instance, it's not larger than. So we failed to reject the null hypothesis. So in step number 7, I write it out and speed forward so you don't have to watch me write. So I have there's not enough evidence in the data at the 5% level of significance to show that the population that have had surgery for peripheral vascular disease who believe that continued smoking puts them at risk for amputation is not 0.6. That's what we have. So what we'll do now is let's see what ChatGPT says about this. So I've used ChatGPT here, and this is my prompt. You can of course see I'm using ChatGPT 0.3 mini high. By the time you watch this, we might be many generations into the future. But here we go. Help me with the following biostatistics example problem. So I preempted with this bit. Then I copied and pasted my problem. The proportion of the population of people who've had peripheral vascular surgery for peripheral vascular disease due to chronic arterial insufficiency who believe that continued smoking puts them at risk for amputation is thought to be 0.6. Researchers collect data from 100 random subjects in the population, so that specific population, and record that 55 believe that continued smoking puts them at risk for amputation. The researchers want to test the claim that the population proportion of people who have peripheral vascular disease due to chronic arterial insufficiency who believe that continued smoking puts them at risk for an amputation is not 60% at the 5% level of significance. Now use the chi-square goodness of fit test for proportions to test the claim that the proportion is not 60%. So that was the problem that I copy and pasted. And what you will notice, of course, is these dollar symbols. Now that is LaTeX or LaTeX as the people who created it. I think they pronounce it as LaTeX or LaTeX. Anyway, that's mathematical typesetting. So in scientific computing, if we want to write documentation to get nice mathematical output, for instance, the formulas that you see, we use LaTeX. And we indicate that the inline LaTeX notation, though, by putting dollar symbols directly and following any of the code. So I've put that, and look at this one, for instance, here, chi-squared. That's how you would write chi-squared. There's a specific keyword for that, chi. And then to get the square, I use that caret symbol, and then I put the 2 inside of curly braces. Now, I only have a single value there, 2, so strictly speaking, I didn't need that. But it is very nice. You can imagine if you have a complicated mathematical formula, it's nice to put it into a chatbot. Now, I have found that ChatGPT is particularly good at reading LaTeX. So if I want to put an equation in here, very nice. Much better, and at least in my experience, than the other large language models such as Claude or Gemini. And anyway, if you want just a short video on the basics of LaTeX mathematical typesetting, it's very easy to learn. And once you have, you'll find it very useful. Just let me know in the comments down below. So that after having copy and pasted my problem there, I added this extra bit, generate a solution to this problem using the following 7 steps. And I outline the 7 steps that we follow in this course. So let's see what ChatGPT came up with. So for the parameter of interest, it said the population proportion P correctly of patients, people who've had peripheral vascular surgery due to chronic arterial insufficiency who believe that continued smoking puts them at risk for amputation. Quite correct. The hypothesis, P is 0.6. Alternative, P is not 0.6. So that's absolutely correct. The level of significance, it writes there little alpha and 0.05. By the way, see how nicely it renders alpha there? And behind the scenes, there's some mathematical typesetting there. and that's $, and it's \ALPHA for alpha, and another $ symbol, and that generates the alpha. Very nice. And as I say, for me, ChatGPT is very good at mathematical typesetting. What statistical tests and assumptions? It says we're going to do a chi-square goodness of fit test. Strangely enough, it didn't put chi, the symbol there, but anyway. The assumptions then, we have 100 subjects who were randomly selected. Each subject's response is independent of the others. Good. Expected frequency, and you can see there the expected frequencies are 60 and 40, and that is at least 5. And so we have no problem using the chi-square goodness of fit test. So the test statistic, believe O sub 1 is 55, do not believe O sub 2, that's our observed value 45, expected would be 60 and 40. Just as we said, it doesn't show us how it does that calculation, but I think I would have liked it to show how you do that calculation, just n times p sub 0 and then n times 1 minus p sub 0. Anyway, we have a nice mathematical typesetting here of our test statistic. They've plugged in 55 and 60 and 45 and 40, so that's all well. And ChatGPT gets a solution of 1.0417, just as we did. Degrees of freedom, it also has 1 degree of freedom. And so for decision rule, for a chi-square distribution with a single degree of freedom and an alpha value of 0.05, that would be approximately 3.841, just as we said. And if x squared is computed to be larger than 3.841, we would reject, otherwise we do not. Our calculation shows it's not larger than 3.841, and therefore we failed to reject the null hypothesis. And then at the test conclusion, I will leave you to pause and read that. I think that's absolutely fine. And so, yeah, I would give 100% here to ChatGPT. Well done. So I show you this full on knowing that you are going to use this to verify your work. If you just use it to do your work for you, you're not learning anything. And I have no fear that you are using it in the wrong way. That you are, and I have full belief that you are using it to verify your work or even to generate problems so that you can practice. So I have no problem showing this at all. Now I went one step further for this problem. I said, please create a plot showing the chi-squared, there's my chi-square notation, distribution on 1 degree of freedom with the region of rejection above the critical value for 5% level of significance, and include a marker at the test statistic value of 1.0417 to show that it is not in the region of rejection. And so what ChatGPT did is it went ahead and wrote me some Python code. Now I copied and pasted this. There's a nice copy button there. And I just copy and pasted into Google Colab, a Google Colab notebook. Once again, if you want to see videos on just how easy it is to use Google Colab, that is just something that you can use in your Google documents. So in your Google Drive, you have Google Docs, Google Sheets, etc. But there's also Colab. Little comment down below, and I can make a video on that if you're interested. There is my notebook, and I've just copied and pasted the code in this notebook, and I've executed that code. It's very nice here in Google Colab. You don't have to install Python at all. I've copied and pasted that. I've clicked this little run button that you can see up there, and look at our nice problem there. You can see there's our chi-square distribution in blue. And if you look very closely, you'll see right at the bottom, there's our little region of rejection in pink there. And this line that it's drawn there, that's our critical value. And this green one, that's our test statistic at 1.0417. So clearly not in this region right on the right tail here from 3.84 towards positive infinity. That's the 5% least probable x squared values under the null hypothesis. So again, ours falls here in this 95% region of the most probable 95% of x squared values under the null hypothesis. So we failed to reject the null hypothesis. So once again, very nicely done, ChatGPT. Leave me a comment down below. Do you use ChatGPT for this? Do you use another model? What is your experience? What is your feeling about its use?